Okay. All right, Brian, thanks for.
Well, first I want to welcome everybody. And as JP said, feel free to interrupt me and ask questions at any point. Although this particular talk, there probably won't be a lot of questions. It's pretty simple, straightforward things about how to make quantum materials or how to make any material. And really the sort of mistakes that you can make when you try to do this. Does that not work? So this is kind of the outline of what I'm going to cover in the next hour or so. I'll give you an overview of my group at Oak Ridge, the sort of things we work on, the capabilities that we have, so you have some idea of sort of where I'm coming from. And then I'll go over some of the basic things that you have to consider if you're going to make a new compound, particularly one that's not been made before in single crystal form. So there are things like, which should be, pretty straightforward. The starting chemicals that you use, why it's important to weigh things at every step of the process, the importance of writing everything down in your lab books, even things that you think may not be that important. I'll give you a couple examples of when this is really important. Talk a little bit about phase diagrams. This is particularly important if you're growing things by flux techniques, for example. Talk a little bit about crucible materials, how to scale up to grow larger quantities of materials, particularly larger single crystals. At Oak Ridge, we have a lot of neutron capability. And to do inelastic neutron scattering, you typically need a crystal about the size of your thumb. So that, for a lot of materials, is difficult to do. I'll give you some examples of how that's done. I'm also going to talk some about a sort of a new crystal growth method. It's sort of a variation of a vapor transport, except using liquid rather than a vapor. This was developed by Xiaojin Yan, who's in my group. And then talk some about the importance of characterizing what you grew, both in terms of its purity, defects, general properties, and why it's extremely important to do this before you start writing a paper about all the wonderful physics that you see. It's really important to know what it is you're measuring. And this is a phrase at the bottom that came from Hume Rothery's book. Hume Rothery was a pretty famous metallurgist. The book was published, I believe, in the 1930s. But in the introduction, he talks about physicists often make beautiful measurements on crappy samples, and metallurgists make crappy measurements on beautiful samples. And so part of the point of this talk is to get you to make samples like a metallurgist, but then measure them like a physicist. So this is the current group at Oak Ridge. There's myself, there's 5 staff members, plus David Vandris will be talking a little later this week on vapor transport growth of 2D materials. We have a couple of neutron guys, Andrew Christensen and Joe Pattison, and 4 postdocs at this point in time. It's a very talented group of scientists. Some of the names you've seen, like Michael McGuire, Xiaojin Yan. It makes it very easy for me to manage them because I just say, well, they're the labs. Go do something to make them proud. But this is the group that we have right now. And what we typically work on, in the past, we've worked a lot on thermoelectric materials, some on superconductors, some on permanent magnets that don't use as much neodymium or dysprosium, which are critical elements in terms of their availability on the Earth. We've also worked on a lot of materials with unusual magnetic ground states. And our recent research has focused primarily on quantum systems, things like quantum spin liquids, or cadmium metals, or honeycomb materials. And so typically what we do in the group is we first decide what we want to grow. We grow it, we measure its properties, see if it's interesting. Measurements. So this is just a picture of some of the things that we've grown. Some of these are pretty old, about a decade. Like there's one on the iron silicide doped with iridium. And these are grown by all sorts of different methods. There's a floating zone, actually in a high pressure floating zone furnace up there on the upper left. Let's see if I've got my laser pointer here. So this is grown at an oxygen pressure above 60 bars of oxygen gas. The system we have goes up to about 100 bars. So this is essentially the pressure in an oxygen gas cylinder. We can apply that pressure while we're growing by the floating zone technique. This is a pretty famous example of a cleavable ferromagnet. This was first shown to be ferromagnetic in one single layer, atomic layer thick, of chromium triiodide. This is a crystal of a ruthenium trichloride, which is a possible quantum spin liquid. And this is one of the old iron-based superconductors. And there's just a variety of different things. This is a tunable, cleavable ferroelectric material here that's also from single crystal form. So this is, sort of some of the things that we work on. You have a question?
Yes. Do you have any sort of advice for taking photographs of crystals? These are really nice.
Yeah, well, these are some of the better ones that we have. I have a lot of really bad photographs of crystals. You can get professional help at Oak Ridge, I'm sure it is too. But a lot of these are just taken with the phone. The lighting, of course, is important.
Looks like pennies are very important.
What's that?
Pennies.
Yeah, just to give you a size. Most people know what the size of a penny is. If you put like a grid like here, it's not clear. You can see the tweezers. But yeah. Yeah, I have several photographs. I think I took this one. I'm kind of a penny guy. A lot of the other guys use the round. So there's a lot of different ways that you can grow single crystals to make materials. And this is a table that was taken from Pamplin's book on crystal growth. Which is a good reference book for a lot of different ways to grow materials. And there's things you can grow out of the solution growth, like floating zone, flux growth. There's vapor phase transport. There's a solid state growth, and there's no growth. This is just sort of some of the ways that you could prepare a single crystal. And single crystals, of course, are important because a lot of the materials we studied are not cubic. Most of the interesting ones that we're studying are actually hexagonal. And so the properties vary depending on which way you apply the magnetic field or the electric field, depending on what you're measuring. So a single crystal is very important. It helps you understand better the physics of the material. So the question, of course, is you have a compound you want to grow, what technique should you use? And that's sometimes a tough decision. And I'll have to admit that a lot of times we'll go with the simplest technique first to see if that works, like vapor transport, where you just basically seal up a quartz tube, shove your ingredients at one end, put a temperature gradient across the tube, put it in the furnace and see what you get. Flux growth, I do a lot of. That's a pretty powerful technique. It's sort of like the old technique of like growing salt out of water, where you saturate the solution in a water up, say just above room temperature, and then let the solution cool down when you hit the solubility limit, and then crystals will start growing out of solution. You do the same sort of thing with what we call flux growth, except the solution can be like a metal, like tin, for example. That will replace the water. And then there's the floating zone technique, which is good, particularly for oxides, but also for a good number of intermetallic compounds as well. This is good for high melting point materials where you can't really use a crucible because the crucible will react with the material you're trying to grow. And I'll talk a little bit about this later. But you have to really think about what you're trying to grow, what's available in the literature. The literature can also give you some ideas about what might work. You can look at papers that were in the 70s or 60s. Sometimes get a good idea of how to grow it. But that's one of the first questions that you have to answer once you've decided on what material you want to grow. This is our floating zone area at Oak Ridge. We have 3 floating zone furnaces. I've got an example. Laser pointer.
We're trying to get another.
This was I brought, but it's just the contact. Anyway, the upper left, that's a 4-mirror furnace. That was used, it's got some magnetic seals, which allow you to get a much better vacuum than, for example, the NEC furnace, the thing with the gold plating over on the right. And so this we grew some iron sulfide with various things. This has iridium in it. The NEC furnace on the right is the oldest one. It's probably the best for growing oxides of material as long as it doesn't melt at too high a temperature. I mean, it'll go up to a couple thousand C, but if you get much higher than that, you have to use one of the other furnaces. And this is a manganite crystal that was grown in that furnace. And then this is the newest furnace that Dutch Yen got with some DOE special grant money. It's a high pressure floating zone furnace that allows you to control a lot of different aspects about the growth of the crystal. It also goes up to higher temperatures. It goes up to 25, 2700 C. This is a barium iron oxide compound that was grown in this furnace with, I think the oxygen pressure was about 100 bars for this growth. So that's one capability we have here. This shows a floating zone growth in progress. You probably can't tell, but the bottom rod is rotating this way, so we'll call that clockwise. The top one is rotating counterclockwise. And so the liquid is in the center. And what you do in any sort of floating zone technique is you have a energy source, in this case is a high-powered lamp, which you can then focus on these 2 polycrystalline rods that you have to make. And they have to be pretty dense and uniform before you put them in this system. And then you focus the light from these high, a couple kilowatt lamps onto this region. And then you basically melt the 2 rods together as they're counter rotating. And then you slowly translate this liquid zone all the way up the rod. Yeah.
That's sped up, right? That's not real time speed.
I think that is real time. It's the video you didn't make, yeah. That looks about right. Actually, you rotate them faster than that too.
Yeah.
Yeah, but I mean, this is a nice technique, but it takes a lot of work because you have to make these polycrystal rods, which are these sort of gray things at the center. So you have two of them, one that you start the growth at, and then a long one that you translate the liquids in along. And if you're lucky or good at this, you can sort of neck it down and end up with one. Yeah, go ahead, one crystal.
So these rods, are they polycrystalline of the sample you're trying to make or of the starting elements?
I'm sorry, ask it again.
Polycrystalline in that you made the sample that you want to make, it's just a polycrystalline version.
Yeah,
of it?
yeah, exactly. Yeah.
How big do they have to be for this? Like, how big do you need to make the rod?
I'm sorry.
I'm sorry. How big does the rod need to be?
Well,
Or what's
as
the
long as you
minimum
can
size?
make it, yeah, that will give you a much better chance. The diameter is important too. It's harder to grow single crystals if it's too thick. So typically they're like 6 millimeters, quarter of an inch in diameter, and maybe 20 centimeters long. Yeah, but you really have to want to grow something to do it this way because there's quite a bit of work involved. And there's a lot of this thing can fail pretty quickly, and you have to start all over again. But it is a very clean way to grow something like this, which melts, above 2000 C, because there just aren't that many crucible materials that you can use that won't react with material that can go up that high. This is some of the other capabilities of the group. We have a couple of different arc melting systems. Arc melting, which I think is part of the practical, you guys will get to see this. This is the fastest way to mix conducting elements together. You have a, this is really annoying.
Does anyone have a laser pointer?
Works.
I know, grab one. We'll try to get one.
Okay. Well,
You can also use the mouse.
yeah, I can use the mouse. I can't stand here and use the
That's
mouse.
true.
Anyway, there's a water-cooled copper hearth. And then above it, there's like a tungsten tip. And you end up, it's got argon gas in it, you end up creating like a plasma. And so this thing focuses down on what you're trying to melt. All right. Thank you. Appreciate it. So this, yeah, there we go. Anyway, so there's a little tip here, and you basically just take chunks of what you're trying to melt together and set it on the copper hearth. Make sure the water circulation is good, and the hearth is clean. And you can make a lot of different materials by just melting the material together. The modification of this, you can form what they call it, I believe, a tetra arc. You have more than one of these tips. You can actually pull a single crystal out of a little melt. But this is typically used for making polycrystalline material first, just to see basically what the properties are. There's some capability you can drop cast rods of different diameters, which you could then put in the floating zone first if the rods are good enough. And we also have a very large old system, which is a arc melting system connected to a welding power supply. And so in this anti-chamber, that's where the arc melting goes. This is the tip sticking up here that goes down into the chamber. And there's a glove box over here, so you can actually work with elements that are fairly reactive, like barium, for example. You can then transfer the barium into and put it on the hearth and melt something. We also use this a lot if you want to make samples inside sealed tantalum tubes, for example. This is a good system for sealing the tantalum tubes. We have a room that just essentially has resistively heated furnaces. This is an older picture. There's a lot more furnaces in there now. But this is typically for flux growth, which I'll talk about a little bit more in a minute. some have silicon carbide heating elements, so you go to 1500 C. Some have one with disilicide, go to 1700 C. And a lot of these just have a nichrome type heating element, which goes up to about 1200 C. But these are used a lot. We also have in the same lab systems for growing crystals via the Bridgman technique, which is essentially you have a pointed silicon ampule, you melt all your material inside the ampule, you have a liquid, and then you slowly lower it down through the furnace until you hit a cold region, and then you get a crystal that nucleates at the point of your silicon crucible. And then you get if you're lucky, a single crystal. Here's a silver antimony telluride crystal that was grown. It's like 5 or 6 centimeters long. It's grown in the system. We also have a couple of furnaces that are for more traditional solution growth, where you use water or deuterated water to grow crystals. This is a crystal, interesting magnetic, I believe it will be ferroelectric too. So this is nitrogen, deuterium, iron, fluorine, and deuterium. Deuterium, of course, is for doing neutron scattering. You have a lot of hydrogen in your sample that gives you a signal which is difficult to tell what you're looking at when you do neutrons. So metal flux growth, this is kind of my favorite technique because it's quite versatile. You can do a lot of different things. And so this is typically what we start with. This is the penny again, so you can see how big these things are. This is about 2 cubic centimeter aluminum crucibles. There is a ceramic piece in the middle, which has a bunch of little holes in it. So you can buy this set for not much money from LSP Industrial Ceramics in New Jersey. And it's called the Canfield Crucible Set because Paul worked with the guy who runs the company who produced these. And these are really nice, relatively clean ways to do flux growth. They're typically, for example, if you're growing a crystal of manganese bismuth, you put a little bit of manganese and a lot of bismuth in this crucible. You put the top one, and then you put this other crucible on top, so it looks something like that. So your material's in here, then you put all of this into a quartz ampule, put silicon quartz wool at the bottom and at the top, and then you seal this. So you have to be careful you don't turn it upside down. Although if you have enough quartz wool, you can even do that. So these can't move. But then you take this, and then this is how you seal it. This is a sealing station in my group. We have 3 of these different ampules. There's mechanical pop down here. You can also backfill with argon or helium, whatever you want, or just leave it in vacuum. And this is Byram Safarov sealing one of these flux growth. There's a couple of aluminum crucibles here, and he's sealing it off from air using a hydrogen oxygen torch. And this system is very simple. These are all commercially available valves and parts. So it's easy to take apart, easy to clean, which you need to do on occasion. So once you've got your materials sealed up, and so this is, I think this looks like one of my seals. It's not as pretty as some of the other guys in the group. There's something called the 4-fold way of sealing crystals, which is pretty, it's a pretty easy technique to use once you get familiar with it. It allows you to seal this off on your vacuum. So you know that the temperature you need to go to, you know how you want to cool it. So you take this, put it in a large aluminum crucible. This is just a heated furnace, goes up to about proceed. Go through the temperature cycle. At some point, what you should have are crystals inside of a liquid. In this case, it'd be bismuth if you try to grow magnesium. So at say 250 C or so above the membrane where this is bismuth, you take this out, throw it into the centrifuge, and then you would take the extra flux, which in this case would be mainly bismuth, and centrifuge that into this second crucible. You know, crystals stay behind, sort of undisturbed. And if you're lucky, you'll get some, reasonably nice crystals. So this is several millimeter manganese bismuth crystals. Here's some cadmium silicon biphosphide crystals. These were grown probably 15, 20 years ago. I don't remember why I grew them. Yeah.
Sorry, I missed the, what was the reason of this fourfold seal?
Structural. Well, I'm sorry, what was it's a threshold?
Is it for structural purposes or?
Yeah, it's as you know, sometimes it's hard to seal these silica tubes as they get large in diameter. At some point, we have to get a glass shop. But this fourfold way is a pretty simple way to do it so that you get a good seal every time. Because this pointy end, which usually gets rounded off a little bit with a torch, that's what gets thrown into the centrifuge, which usually has core 12 at the bottom, but still, you don't want to snap this off when you try to. Yeah.
Can you go back to the slide where you have sort of two crystals inside the tube?
I'm sorry.
Slide.
Oh, okay.
This one. So why are two crystals used in that picture at the bottom?
Why are there two?
Yeah, there are two crystals.
Yeah.
used.
Okay. The crystals will grow in the bottom, but once you're to the point where you have crystals and a liquid, you want to get rid of the liquid. And so when you put this in a centrifuge, the liquid goes through this ceramic piece, which has, you probably can't see it, there's a bunch of little holes in there which allow the liquid to easily go through it. And your crystals hopefully are too big to go through the hole too. So that's kind of what we're trying to do. You can also, if you don't have this piece like this, you can put just some quartz wool, sort of fill this up with quartz wool. And then the liquid will go through quartz wool, but it'll catch your crystal. That's why they're two.
Thank you.
Yeah,
And then this metal flux, that's the liquid.
that's the liquid, yeah. Okay, so that's kind of what our group does in a very general sense. Now I'm going to go through some of the basics. Starting chemicals. We think, well, you just buy the chemical and you have it, and so you use it. Well, that works for some things, but it's good to know a little bit about the properties of the material and how careful you have to be with it. There's something called the material safety data sheets, which have probably every possible way that this thing can be dangerous. Like helium gas is pretty inert, not that dangerous, unless of course you fill your room with helium and you can't breathe. No oxygen. But I don't find these things that useful. I mean, they're important to have, but when you're trying to grow something that you haven't grown before, or use an element that you're not familiar with, I find this book, How These Condensed Chemical Dictionary, much more valuable. It's got a very short list about pretty much every element and compound that you can think of, and about what the actual hazard is. What's the most serious hazard? The toxicity level in air in terms of like milligrams per cubic meter. And so if you're familiar with, say, like using lead, and you want to compare that to using thallium, which you may not be that familiar with, you can kind of compare what the difference is between lead and thallium. And that gives you some sort of feel for how to handle the material. There's usually a lot of useful information written on the side of the handle. These are Siberian single crystals, sealed in silicone because barrier reacts very quickly. And it says, irritates skin and contact. So, you want to, if you use barium, you definitely want to have some kind of gloves on. And in this case, you also probably use it in the glove box. Arsenic can cause cancer and a bunch of other things. This is where this book is really handy. It can tell you what are the most common problems with handling arsenic. Arsenic is kind of a funny element. You can buy it and store it in the glove box, but you can actually weigh it pretty easily. It doesn't oxidize that fast. But if you let it sit out for any length of time, it will eventually turn black on the surface as a formation of arsenic. So, these are sort of things that you learn over time to make it. As I mentioned, a lot of the starting materials have to be isolated from oxygen, in some cases water as well. These are very nice glove boxes manufactured by M. Brown, which is a German company, but they have a U.S. representative, I believe they're in Maine. They have a nice readout, so that this is, water and oxygen content less than 0.1 part per million, which is pretty good. And so a lot of the lighter rare earth metals, a lot of alkali metals, some alkaline earth metals are all sorted here along with some of the compounds that we made previously that are reactive with air. But these are very nice glove box systems to have. I think we have 3 of these, two the size of the So you buy this chemical, and the vendor says, okay, you've got 200 grams of tin, a little tin shot. Over about 40 years of doing this, I've run into at least three situations where the label on the bottle was completely wrong. In one case, they actually said zinc labeled at 10. For some reactions, that is a real problem because zinc has a much higher vapor pressure than 10. That could have caused an explosion if you're not aware. So it's good if you can to check to make sure that the compound that they sent you is really what you got. Or the element that they sent you. The other thing is that the stated impurity, so that everybody wants to put 99.999% on their elements or compounds. In the case of ruthenium trichloride, they don't even check for oxygen or carbon or a lot of other elements. And so when we first tried to grow single crystals of ruthenium trichloride, it says 99.99% metals basis, which means the metals that they check for purity. But if you actually X-ray it, analyze it, you've got ruthenium oxygen chloride, another ruthenium oxygen chloride, and ruthenium metal. There was only about 20% of all of the material was actually ruthenium trichloride. So we had to obviously fix this. This goes back quite a ways to the time of the cuprate superconductors, when I was trying to make an neodymium copper oxide material. We had a huge, like 5 kilogram or 3 kilogram container of neodymium oxide, a nice light blue color. But I tried to make it with this, about 30%, maybe 40% of the weight of this powder was actually water. So if you dry the material, in this case, heat the neodymium oxide up in a furnace above the 1 point of water, the light blue powder turned into a dark blue powder, which was then good to use. So if you have a very old chemical, it's good to also check to see what you've got. And I'm not going to talk much about this, but if you grow crystals out of an organic flux, there's a lot of low-dimensional magnetic systems, which have lots of organic ligands sort of spacing out the magnetic ions. Most of these organic compounds have to be filtered or purified further. What you get from the vendor is not really the compound that you're interested in using. So if you have an organic chemist, you can go talk to him about using these things, because he should know how to purify. Weighing things. I know, I guess Manders isn't here yet. He used to kid me a lot, because it's amazing what you can do with careful weighing of your reactions in different steps of the way. And Antoine Lavoisier, who was a pretty famous chemist, one of the fathers of modern chemistry, provided tremendous insight into a lot of different chemical reactions that we think are trivial at this point. But at that point in time, it wasn't clear what happened when iron oxidized and turned brown. It's just picking up oxide from iron oxide now, but that wasn't what they thought was happening at that point in time. And so by being able to weigh things very accurately, and this is kind of a crude picture of his balance, where you can actually weigh different reactions as you're doing the reactions, so you can get some idea of what's going on. Of course, today we sort of use like a TGA or something to do this. But it gives you tremendous insight and confidence and control over the quality of the final crystal. If you sort of know that things are happening as you just expect. Like if you're using a carbonate, you expect the CO2 to come off. But does it really come off? By weighing it, you can tell. This is a surprisingly simple but important thing to remember. When you're growing a crystal, particularly for the first few times, it's really important to write down everything you can think of that might be wrong. For example, the furnace that you use, the growth parameters, the atmosphere, the crucible types, the weather in some cases can make a difference. And this is something that I've found to be very true. Sometimes you grow a really nice crystal the first time, and then you try to tinker with the recipe to make it better. And then 6 months later, you're sort of back to the original recipe, more or less. It's really important to write down everything you did. And I'll give you an example how important this can be. We grew the first sort of sizable crystals of manganese bismuth that had ever been grown. This was only done about 5 years ago. And I'll show you why we haven't been able to grow these in the past. At least one of the reasons, anyway. So here's manganese bismuth. This is a ferromagnet. The Curie temperature is well above room temperature. And you can make this into a permanent magnet. And they actually sold this commercially as a permanent magnet in Japan under something like bismuthol or something. But to grow this, the first thing you do is you get, this is a phase diagram for Locomotive, and it typically has all or almost all of the binary phase diagram between any two elements in the periodic table. And so if you go to 153, that's the bismuth manganese phase diagram. Here's the corner. Pure bismuth is over here. This is the compound you're trying to grow, manganese bismuth here. And you've got a pretty narrow temperature range, it's about 90 degrees. You can grow this thing in. So this line here, everything above that line is liquid. So if you start with a composition where this red arrow is, as you cool this liquid down, you hit this line, you'll start precipitating this phase over here, which is manganese bismuth, along with more liquid. So you cool it down to above this 262 C line, and then spin the excess bismuth flux off. So this is the recipe that was used. A lot of bismuth, not much manganese, because you're over here close to pure bismuth. And typically take things up to a really high temperature to make sure that the liquid is mixed well. It stayed up there for 24 hours at 1,000 degrees C. You can see this is liquid, low 400 C at this composition. Then you cool down fairly quickly to 400 C, and then very slowly you cool down through this region about ½ a degree an hour. So this takes a week or two to do. And so the first few grows, I got really nice crystals. These are several millimeters on the side, which is much larger by a couple orders of magnitude than what had been reported in the literature previously. And in one growth resulted in one crystal, which went all the way across this 10 cc aluminum. And it had a weight of about 1.9 grams, and this was used for spin wave and polarized neutron study to map out magnetism. So this was done, and then about 6 months later, we had run out of these crystals and said, well, we'll just go some more. And went in and tried to do this, and all the crystals that I got were much, much smaller than 1 millimeter. They were typically like 100 microns. And so the question was, what happened? I followed this recipe, and we struggled. Well, I struggled with this for quite a while, trying to figure out what the difference was. We tried different chemicals, varied this recipe a little bit, but nothing seemed to work. So then I went back and looked at the original notebook. What I found was that in this case, I also swirled and shook the growth at 1,000 degrees C. So basically I had gloves on and a long set of metal grips, which you had to grip the growth and just shook it. It turned out that was the key. That even at 1,000 degrees C, 24 hours, the liquid was not that homogeneous still. And once I did this, I started getting the big crystals again. So that's, I was happy I wrote that down. It's kind of scrolled in the top of my lab note. Crucible selection. So if you want to make something, you have to put it in something. You're going to heat this up to some high temperature. There's a lot of different crucibles you can think about using. We typically use aluminum oxide, silicon dioxide, tantalum metal. Never tried boron. There's several that you can use. The literature, vitreous carbon is pretty good for something. Yeah.
I know it takes slides already from the previous reaction, but I had a question on why you stayed at 1,000 degrees C for 24 hours. Because typically people stay that high for homogeneity purposes, but your swirling technique kind of proved that there isn't homogeneity at that point.
Yeah. It has to do with, in this case, with the ability of manganese to diffuse in this liquid. It's apparently not very fast.
So then you would have little wells of pockets of a different type of gradient within bismuth.
Well, yeah, the manganese, my guess is, obviously I don't know, I just did this and it worked. And that's the other thing. We don't actually study in great detail how the crystals grow or what the mechanism is. But my guess is that it's just not a homogeneous liquid. And so there's a lot of different places you can nucleate manganese bismuth crystals because of the gradient. And that gives you, if you have a lot of little teeny nucleation, little tiny crystals of manganese bismuth, that limits on how large your biggest crystal can be.
follow-up question. You previously said that flux growth is similar to the saturation of water with salt.
Yeah.
And you made the point that manganese doesn't diffuse into the bismuth well. Where do we get that information in terms of solubility and diffusion rate in the liquid from metal to metal?
Well, the sun, yeah, I mean, that's why the phase diagrams are extremely useful. They tell you what the solubility limit is, or what phases you're going to get at a particular temperature. And so if you look at these, once you get used to looking at these phase diagrams, you can kind of tell if there's a liquidous region which precipitates your crystal first, that's where you want to be. At least that's where I want to be. There are probably other ways to do it.
Thank you.
Okay. So there's a lot of different crucibles that you could use. You use aluminum a lot. Maybe manganese oxide. And there's also some metallic. So how do you decide which one you should use? Well, as it turns out, this has been looked at in the past. And this is from a book called Intermetallic Compounds. It was published in 1967. And at that point in time, there was a lot of industrial research in crystal growth and in general. And in the book, everybody got a copy of the book, right? In chapter 1, this table is reproduced toward the end of the chapter. But it tells you, for example, like for alkali elements, which are very reactive, you can use pyrex or silicon at low temperatures, steel at high temperatures, for example. And it also tell you what the protective atmosphere should be. And this is a good starting point for guessing what sort of crucible you might want to use to grow your material. Because typically you start with either elements or pretty simple compounds. And this goes on for rare earths, silicon germanium. So it's got pretty much all the different elements that you can work with. So this is a good way of deciding which material you should use. Yeah.
So you have about 5 minutes, but I have a question.
Yeah.
I saw thorium oxide. Have you ever used thorium oxide?
No.
Does it
Yeah,
sound very
it's pretty hot.
Yeah.
I can tell you a story about this sometime. Okay. We have a really nice glass shop at Oak Ridge. Most of the labs do. A lot of universities also have a good glass shop. And you can make specialized ampoules like this one here. There's a long, skinny tube here at the end. So you fill this material up, this ampule up. You say here, when you melt the material, the liquid line will be here, and you have liquid all the way down. You then lower this through a temperature gradient. Material here will freeze first, and you should get a single crystal which propagates all the way up through the rest of the year. These black ones here, sometimes you'll have elements that react somewhat with silicon, but maybe not too badly. And so what you can do is you can put in a little acetone, dump out the liquid, and then put a little top up here, and just heat this with a hydrogen oxygen torch, which will then pyrolyze the acetone and deposit the graphite all along the inside of your crucible. So in some sense, you then have a graphite crucible inside your silicon. And this helps for some rare earths. If you use larger ampules for flux growth, like I often use these 10 cc crucibles. You put quartz roll on the top and your reactant at the bottom. Glass shop makes these things for me. It's two pieces. It's a little top and a bottom, and they actually will seal this under vacuum for me, keeping the bottom cool. This is the sort of thing that is very difficult to do, even if you're pretty good with working with silica and a high complexity. Here's a larger one with 50 cc aluminum crucibles in it. Scaling up. Jeff will appreciate this. So in trying to grow a slightly larger crystal so you can do neutron scattering, particularly inelastic neutron scattering. So here's the 10 cc, the 50 cc. This is the largest crucible that fits in sort of a standard centrifuge. Most of the centrifuges I've seen don't have anything much bigger than this size. And so, in the case of manganese bismuth, you can grow 40 grams of material, out of which you get maybe a couple of grams of manganese bismuth. So the glass shop is very helpful as long as the elements that you're using don't react really bad with air. Now, if you're trying to grow something on sodium or an alkali metal that's very reactive, you can't do this because they're sealing this off. Well, they're putting the top back on in air, then they pump it out. They seal it. This is, I think, the largest that they can do in a glass shop. So this was a 250 cc platinum crucible. Inside here, there's my hand. This was used to grow potassium vanadate crystals, which is a nice sort of 2D magnetic system, using a KBO3 flux. You don't have to spin the flux off in this case. You actually dissolve the flux off in warm water, leaving behind this black potassium vanadate crystals. This is something which I've only used a couple of times to grow one particular compound. It's basically a 5-gallon, I guess it's a 5-gallon bucket. There's a stainless steel crucible here. It's got some fire bricks inside with a hole so that an ampule like this size can be thrown in there. But there's obviously no centrifuge associated with this. So when I was pitching softball, this was pretty easy to do. You grab this red, take your thing out of the furnace, put it in here. You have to loosen up to do this before you start doing it. And you just spin it around. That actually works. I know it looks a little crude. Just make sure you have all the safety stuff in case something breaks. But you can usually get a crystal big enough in the centrifuge. Now I'm going to talk a little bit about this new crystal growth method that Yen came up with. I forget we were trying to grow, I think it was aluminum antimony. And the reference for it is here. I think that's also in that first chapter. But he's probably one of the most talented crystal growth guys in the world. Really good at coming up with interesting, strange ways to grow crystals. So it's kind of a flux growth in a horizontal configuration. So here's what you have for vapor transport. You have your starting material. Often it's at the hot end. You have a transport agent, something like iodine. And your crystals go with the coolant. In the liquid transport, you've got your solid material, your starting material, some sort of a flux and crystal growth over here. But a lot of this is all in liquid, so the diffusion takes place in the liquid. So the question is, why would you use this technique versus that technique? Well, this is a compound that we were very interested in at one point. It's a superconductor below a couple Kelvin. We think the superconductivity may be unusual. And so we were trying to grow a large enough crystal so we could do a neutron experiment to look for what is called the resonance, which is an indication that the superconductivity is unusual. And so this is the thermal conductivity at constant temperature. You can see it comes down, and at TC, it starts going up. Phenomenologically, that only happens in superconductors when the pairing mechanism is not just electric. It may be magnetic pairing or something else. So we thought that this was very interesting, and also looked at the phase diagram. So there's a structural phase transition cubic to tetragonal, where there's in this structure there's molybdenum, which along one direction can dimerize. And that's what causes it to become tetragonal, and then it can become superconductor down here. So this looked vaguely like something that you might see in a cuprator in our case. So you need grams of crystals, however, for elastic neutron elliptical resonance. So if you typically use 2 cc crucibles, you have 4 gram batch, 60 milligrams of molybdenum, may get 0.1 grams of a crystal. So if you want to get several grams, you need at least 20 gross if you do it at 2 cc. And here's a picture. Let's see, this is a 10th of an inch. I don't know why it's inch a grid, but this is one of the crystals that was grown using the normal vertical growth configuration. But it's still not enough mass. So you have to align a lot of these crystals to do so here's the phase diagram. Got molybdenum here, antimony here. This is the only compound that's not 7. There's a liquidous region over here. So we start with this composition. You get to here, you'll start growing some molybdenum 3 crystals. But this is sort of summarizes why it's a problem. So if you use the liquid transport growth, you have a temperature gradient, a horizontal tube, which is shown here, and molybdenum is here. All of this from here is pre-melted antimony, so that's kind of liquid. These are some of the crystals that you get out. This was obviously done a few years ago, about a decade. So in this case, you can get a fair number of crystals, which you can then align since it's cubic to do neutron experiment with. Here's another compound that's interesting. This is iron 310-2. Yeah, go ahead.
For this liquid transport, how much liquid would you need, like to cover half of the ampule? Usually, like there was
You need quite a bit of liquid.
Okay.
But I think it certainly has to be there has to be a liquid region all along the temperature gradient.
Okay.
Yeah, a lot of these have yeah.
Similar follow-up. How do you separate the solution from the crystals?
Yeah, in this case, just mechanically separated.
Okay.
If they're big enough, you can do that. But, or you can actually boil off the antimony. So this is another material, iron 310-2, which is right over here. So there's only like a 40-degree window where you can grow crystals using the composition over here. So you come down with the composition here, and this would be the first thing to precipitate out. But this is pretty far away from the liquidous composition you have to start. And so this is the ampule that was before it was for the growth. So you had iron here, and the rest of this is tin filling up. So that when you melt this, you probably have about half. You can see this is quite a bit of tin. So, this actually grew some decent sized crystals that we use for some neutron scattering experiments. Here's some other crystals that were grown by the same technique, using, in this case, aluminum chloride, potassium chloride flux, things like iron selenium, which is an interesting high temperature superconductor, particularly under pressure. lithium trichloride was grown, osmium tetrachloride. These are just pictures of the crystals. So it's an interesting technique. Uses sort of a comparison of this horizontal liquid flux growth with the vertical growth. The temperature does determine the phases that precipitate. This is just for the phase diagram. You don't have to mix the charge with the flux. In this case, you just put the charge at one end, typically the hot end, and then the flux end. Unlike that for traditional flux growth. You don't have to homogenize at high temperatures to make sure everything is homogeneous. There is a temperature gradient along the horizontal axis, which there's not in this case. This is essentially isothermal. The crystal growth occurs before you actually dissolve all of this. You start precipitating long before this stuff is gone. It's not the case for traditional. And the charge fluctuation is limited by the size. That's not the case here than it is here. So there are some differences. There need to be a few more growths done, probably a little theoretical work to see how well this works. But and in certain things like, how fine should these particles be? Does the surface to volume ratio make a difference? Probably it does, certainly in terms of the rate anyway. But this technique is complementary to the vertical flux growth. So if you can't get this to work, this horizontal method might work. Yeah, that's basically just what I told you previously. Okay, this is the last part. The importance of characterizing what you do. So what I'm trying to do is to keep you from falling into Rothery's trap down here, which thinks that we make beautiful measurements on a crappy sample. So if you grow a crystal by Bridgman, which will give you a very large crystal, you have to at least sacrifice one or more crystals to see how homogeneous it is chemically along the length of the crystal. And ideally, you'd like to look at it with microprobe, X-ray diffraction, and probably some physical property measurements at different points along the crystal. I'll give you an example of a problem that you can have with flux growth. This is a really interesting material I was able to grow up 10 flux, but you have to be careful when you do this because you will have some 10 around and you can't have 10 inclusions, which can cause a problem when you're making measurements. And I've actually seen in the literature things like Physical Review B, which is usually a pretty good journal, examples where there was just amazing properties of this one material. But it was clear, at least to me, what the authors had done. And they had this pages and pages of mathematics trying to explain, why this worked out the way it was. But it physically didn't make any sense. So it's really important to know what you're measuring before you report it. In this case, I think what they were doing was they had voltage leads to measure the electrical conductivity across an antimony inclusion toward the center of the crystal. And for some reason, they put their Seebeck lead, which also measures the voltage, at the ends of the crystal. So the Seebeck could be much larger than you'd expect from the measured conductivity. I think that's all they did. But there was a lot of math which didn't make a lot of sense. The other thing is to make the same measurements on more than one sample. It's really important to know that what you're measuring is really the value of the property you're trying to measure. I'll give you an example of that. So here's this is the last couple of slides. This is an iron manganese phosphorus silicon compound. Yeah.
Sorry, I have a question about that. But when you have these large crystals and you say that there's do you find that it's systematic, like how one end, you have some composition, and then gradually.
Yeah, there's a lot of materials that you grow by gradient. There'll be a gradient composition along the length of the you can sometimes tell from the phase diagram that there's a big separation between.
For the horizontal flux growth in the iron green tin tube, what was the ratio of iron to tin? Was it on the same liquidus curve on the far right of the phase diagram?
Well, yeah, I mean, it's got, if you go to a particular temperature, you sort of know where you are. But in this case, the iron is just at one end, and then you have the liquid, and so it's sort of like vapor transport. The iron is sort of diffusing through the liquid. And eventually, you'll get a high enough concentration at the cold end to precipitate the iron 3 and tin 2.
Not as hard and fast rule for the homogeneous temperature than standard flux.
Yeah, it's a interesting technique. So this is by far the largest crystal of this composition that has been grown. This material is based on iron 2 phosphorus crystal structure, which has a lot of interesting properties. This is a ferrite. The iron, there's 2 different sites. The magnetism is quite a bit different at the 2 sites. And so these materials with not only these elements, but others added are really quite good at magnetochloride materials. These are probably the most promising for using a magnetochloride effect in a refrigerator. But anyway, so with this beautiful crystal, these are some resistivity leads. I measured the resistivity versus temperature. You've seen 0 Tesla. This is the curve. It looks nice and metallic. This is almost 2 microcentimeters of low temperature, which was a concern at that point because that's much lower than I expected. If you apply a magnetic field, you get a really large magnetoresistance. So, according to this data, the residual resistivity is 2 microcentimeters, and there's a 750% resistance effect. However, if you look at this more closely and you actually polish the end of this crystal, you can see there is a essentially pure tin core that you're measuring. Tin's got a very low resistivity. The magnetoresistance of tin is about 50,000% at 4 Kelvin. That's something you really have to worry about. So what I did was essentially just grind this thing down so that you miss all the tin. And then this is the resistivity curve you get when you know that you're measuring basically the whole material, not the tin. So the residual resistivity is 440 microcentimeters, not 2, which is what I got before. And the magnetoresistance is less than 0.04% at 6 Tesla overall temperature. Yeah, this is yeah. And so this is the sort of thing you have to be very careful about when you're making a measurement. You have to really check your material to see what you're measuring and measure and understand. That's it.
Okay, thank you.
Okay, we've had lots of questions, so is there any remaining question? We can move on.
Yes. I guess in general, is the concern about growing bigger crystals or is it about making more pure crystals?
Often it's about growing a bigger crystal. You can obviously get to the same mass by having a lot of little crystals. But for a neutron experiment, you have to line